I want to start by thanking a whole bunch of colleagues and helpers, and of course the funding agencies that are really the real drivers of this work. So let me give you a little bit of a history. We were, the Farside Project is an NIH funded toolkit development project. So we developed a toolkit. It's an open source toolkit. You can learn a lot more about it from this website. Basically, this toolkit was meant for the broad, the broad area of analyzing images that come out of microscopes. So along the way, one of our colleagues came along, Bill Lee at the University of Pennsylvania, and he said, "Badri, can we apply it to histopathology?" I said, "Please educate me about histopathology." I thought I'll pass along that knowledge a little bit to you in case you're not familiar with this field. Histology is a study of tissue, and histopathology is the study of diseased tissue. Now, when you think about tissues, they're living entities, and they harbor a large number of dynamic processes, both biochemical, electrical, and what have you, that are all happening in space and time, and they're all, intricately intertwined. And most diseases are one way or another associated with perturbations, unfortunate perturbations to these tissues. So, when Milind was talking about his Vivoscope, you're talking about finding nuclear detail, right? So that you can actually diagnose what's going on. So I wanted to essentially pick up from there. So in the current day and age when, unfortunately even now, when a patient is detected to have some disease, once you pass the detection stage, you need to get to the diagnosis stage. So if you think about a disease like cancer, or even just a particular form of cancer like breast cancer, it's not one disease, but one of n flavors of breast cancer. You need to subtype them. And in order to subtype them, you have to go one level lower. So you have to look at the tissue. So you take a biopsy specimen, and then you put it under a microscope and look at it. So in the currently what happens is that the histopathologist, who is the practitioner of histopathology, puts a thin slice of the biopsy specimen under the microscope and then takes a look at it and then tries to figure out what subtype of cancer it is, or is that cancer real, or is there something else that's going on. But as we step back and think about it, a couple of things kind of stake out. First of all, the tissue is three-dimensional. He's looking at a two-dimensional slice. The tissue is really alive. He's looking at something that's fixed in death. It's a snapshot in time. The tissue has, tens of thousands of different proteins and other molecular players at play, and the histopathologist is looking at, maybe a couple at the most, right? So obviously he's limited in terms of what he's able to see. So currently what happens is that the histopathologist is looking at these essentially RGB images through the microscope using his eye or her eye, and basically they're looking at cell morphology. What's the shape of the cell? Is it different from what it should be? And occasionally they're able to use molecular information. So they use chemical stains that result in colors. So for example, these differently colored cells here are essentially stained for a molecule known as Ki-67. This was a molecule discovered in the city of Kiev in dish number 67, so that's where it comes from. So phospho-ERK and phospho-AKT are the signaling molecules that are involved in breast cancer. So the presence or absence of these molecular markers is decisive. It tells us that there's a certain gene that's either overactive or underactive, or something or the other. And it can establish diagnosis. It can distinguish between competing diagnoses that look almost the same if you just look at morphology, right? So you can subclassify the pathologies, and you can highlight markers that can sometimes predict response to therapies, right? So for example, if you have a treatment that's targeted, are you able to hear me? I didn't put this thing on. Okay, so let me put it on as I speak. So if you have a treatment that targets a particular molecule, you want to know its activation status. So if you can see that the molecule is activated, then yes, it's responsive, so go ahead and treat that patient with this disease. So now currently, much of this work is very, very human labor intensive. People are staring through microscopes, and they're making subjective decisions. So that as you can expect a considerable degree of variability depending upon how much caffeine someone has had or not had, or where they were trained, or which part of the building they sit in, and if the heater is working properly, or the air conditioner, as the case may be. So the scores that they come up with are quite approximate. They come up with a number like, this is a +3. What does that +3 mean? I don't know. But on any given day, the scores that they come up with are very different from one center to another. And insurance companies are often scratching their heads thinking, should I pay for this or not? And whenever there is an antigen or a particular biomolecule that they see, they'll just say it's positive for this molecule or negative, or maybe it's a +3 or something like that. So there is a definite need to improve the situation. They can only see one molecule at a time, although there are hundreds that are of interest. So can we see the tissue better, and can we make sense of the data better? And can we do it in a manner that doesn't rock any boats? So the histopathology is an established practice. There's a lot of tradition there. And you can't just say, okay, throw everything you've learned and then do something else. You can't do that. You have to do it in a, quote, upwardly compatible way. So how can we do that, right? Now, before we get to that, I wanted to point out that talk a little bit about molecular markers. They're kind of like the silver bullets of the future, right? Or even the present, right? So the presence or absence of certain molecules, or co-expression of certain molecules, if two molecules are present or not present together, right, that's very, very informative. Also, where a molecule is sitting inside of a cell is informative. Is it inside the nucleus? Is it in the cytoplasm? Is it on the cell membrane? So where the molecule is sitting is by itself quite informative. So you need to know where these molecules are with respect to particular cell types. So if you have a biopsy specimen, you want, tumor cells are very different from other cells. There are cells that make up blood vessels, or yet other kinds of cells. They all have different roles in tissue, and you need to know where these biomolecules are relative to the specific cell types that you're interested in. If you're interested in immune cell types, that's all you care about. You're not interested in the tumor cells or something else, right? So in the end, it all boils down to understanding the real biology of what's going on to make a real decision as to what the disease condition is. So imaging systems that lack molecular specificity are not nearly as helpful as those that can essentially can seek out particular molecules that are of interest. So in this business, there are lots of alternative technologies, non-imaging technologies that have been explored, and one of them is this whole idea of gene arrays and protein microarrays. So the idea is you can literally look at hundreds or even thousands of different genes or proteins, their activity levels, which ones are being upregulated, which ones are being downregulated, and so on at once. And that, for a while we thought that all this imaging is going to go away by the time this technology succeeds. That never really happened. And the reason is very, very simple. The reason is that in all these technologies, you're taking a bunch of cells, you're grinding them up, okay? So you're disrupting their structure. You're also disrupting all information about where a cell came from in the tissue. Its location in tissue is informative and useful. That's what the histopathologist is looking at, and you lost that. And of course, you lost all aspects of subcellular localization. So to make a long story short, we're still in business, and imaging still rules. So since imaging still rules, people said, okay, can we improve the state of the art? And so one thing they started doing is they started building scanners, RGB scanners. This is the whole field of digital histopathology, as advertised right now by the major companies. And basically, you've gone from staring through a microscope to staring at a screen, but the fundamentals haven't really changed. There's no fundamental value added. The next step was basically clinical information integration. So all these companies started building servers, kind of like your VivaNet and so on, have networks. And basically, in my crude interpretation, it has set the stage for outsourcing, basically, but it hasn't changed the fundamentals, right? The next step is to add image analytics, so some computerized tools for delineating, various kinds of regions in the tissue. But again, there's not a vast amount of clinical value added. In order to add a vast amount of clinical value, you have to greatly increase the amount of content that's being extracted. One way to do that is to replace the human eye with an honest-to-goodness multispectral camera. And that's one of the things we started doing. And what it does is that it gives us very detailed spectral information, both absorption and emission spectroscopic information. And spectroscopy is the key to chemistry. You want to access the chemistry, and spectroscopy is the key to that, right? These instruments produce a ton of information. So if you're worried about the gigabyte or so of information required to store a whole slide scan, you're now talking, 10 times or more of information there. So the question is, can we make sense of all this data? And this was the academic project that we started out with. And here's sort of the idea. So you take this multispectral data and you can unmix it into channels. Each channel gives you one kind of structure. So one channel